Ba-da-ba-da-ba. Mhm. Okay, sure. No reason for that. I don't know why. Hey, my friend. How am I doing? I'm doing great. How about you, my friend? How are you doing? I'm doing really, really good. It's been a good day today. Good, good, Ben. I hope I got this right. Okay, I do. Okay. Can you still hear me okay? That's okay. Okay, you can hear me good? Okay, that's fine. No problemo. Whoa, whoa. It's all good for me. Excellent. Hello, Gustavo. How are you today? I see we have the regular crew. Okay, got a few, maybe a few new people too. People maybe can't come out during those days. Hello, everybody. Holy smokes, what was that? Um, hey, Ground Kicker. Good to see you again, my dude. I hope you're doing well. Is this for makeup? Yes, it is. You probably got my email there. Yeah, this was because my computer was completely out of commission on Wednesday. So, yeah, that was definitely a thing, and also not a good thing. Oh, um, well, yeah, I sent an email to everybody on their Blackboard account. So, maybe your student email. I know I sent it to everyone. Um, this is gonna be today. Well, it's okay if you're at work right now. That's no big deal. I mean, you can always watch the replay here on Twitch, and I'll also upload it to YouTube as well later on. Well, really? You didn't get an email? Well, how did I receive all of my student emails and you guys didn't? Like, I checked and everything. Hey, it's Toast. How are you, Toast? Okay, that's not a problem. You can. More than welcome to anytime. That's why it's there, so you can get it. You could watch again and again and again. Doing all right. Doing all right. Look at this. We're doing good. We're doing good. Doing good. Oh, I got some music today. This time, good music as well. Let's see. Let's get that going. Where did I put that? There it is. Meh. Juice is the best. Yes. All right, let's try this here with woohoo, hey, hey. Yeah, here we go. Yep. Hello. Hello. Everybody's like that. I don't even understand why. I'm looking at the yeah, I'm looking at the table here. I could see Leicester City really doing well this season. I don't know if they'll have like the I don't know if they'll have the depth, but we'll see about that. One team I thought it was going to do really well this season. I really thought Wolves were going to do much better than where they're than what they've done the first 4 games. I thought Wolves have really come a long way to make it to a mid-table or upper tier finish. Maybe not top table finish, obviously, but I thought that their depth got a lot better. They have Neto now, so really thought that they're going to show up. Hopefully, they prove me right the rest of the season. So I don't, you know, yeah, Villa. I mean, Villa 3 out of 3. Can't really complain about that, but we'll see how long that lasts. LeBron, LeBron James. All right, I'm gonna change out of the sir. I'll be right back. All right, then we'll get started. Okay. All righty, everybody. Let's go ahead and get going here. Okay. Here we go. All right. All right. All right. You. Can you buy me a PS5? Why don't you put up the? Why don't you work for it? Like everything, everybody gotta work for it. What if you're not the best at math? You don't have to be the best at math. You just have to be the best at reading patterns. And if you just read into it, you can make good solid trades. You don't have to be like super great at math. Oh, that already passed. That was last month, my dude. Way last month. Yeah, the side hustle, man. That's like it saved me this year for sure due to COVID and losing job and everything. So it actually wasn't something I was going to go back to. I say go back to because I used to. You just have to strategize correctly. That's all. Thanks, Toast. It's you don't have, you just have to strategize and just it's all about timing at the end of the day. Because I mean, with options you can make a lot, you can lose a lot, but you can also hedge your risk the way you want, so you can determine the odds. No, it wasn't my birthday. My birthday was last month on the 20th. It was quite a while back now. It's all good. Ivan, my friend, I didn't get to say hello. Ivan, how are you doing today? Wait, I didn't tell you. Well, I mean, I don't know. I don't think it's like a super great big deal. So, no problem, dude. I don't know if it's a super big deal. I mean, I turned 41. Yeah. All I had was dinner with my folks. Good, my friend, good. Glad to hear that. Hope you're having a happy Friday. I haven't had a sit down meal with my folks in a while because of COVID, so it was nice just to sit down and have a nice family meal. All right, everybody, let's do this. Okay, we ready? I'm All right. Let's go ahead and get started. Am I married? No. Nope. Don't even have a girlfriend, so not married at all. Never been married, and yeah, have had girlfriends, but never been married. I have plenty of children. As in all of you. How come? I don't know. Just I don't know, just never the right time, I suppose. It's just one of those things that just happened. Yeah. I know. Okay. Okay, let's get started today. Welcome back. Welcome back, everybody, to Wednesday. It's Friday, but it should have been Wednesday. Yeah, that's. No, I don't feel lonely. I talk to you guys. We're sitting and chilling. I got friends, the whole 9 yards. It's just that, I may not devote myself to just one person. I devote myself to many. So sometimes that just is a little better. Um, so I want to first apologize to everybody. My computer on Wednesday absolutely went to the crapper. It was like an hour and a half before my first class on Wednesday, and then yeah, Windows got corrupted, and it was bad. I mean, really, really, really bad. So, um, yeah, that wasn't good. And then I had to send it in for emergency repairs. I knew that I needed a better set of eyes on it than mine because it would take me too long to fix it. So I got a second set of eyes on it. A lot of money, some money later, not a lot of money, but still some money later, it got nice and fixed up and even looks a lot better because I got the person to recable my machine. So now it's not a rat's nest of a machine. Now it actually has like actual cabling that looks nice. Here, I'll show you here. You'll see my crappy ass apartment here. It's not the greatest, obviously. It's not. It could be in dire repairs, but yeah, it is what it is. Okay. So here's my box. It's a thing. Okay. So yeah, yeah. There's my there's my card. Mm-hmm. And how. There's the this is my medicine. I need to move out of the way. And then here's the front of my box right here. Yeah. Here you go. I'll turn it to the side like this. Wonder what happens there. Yeah. Man, I'm so bad with this camera. Holy crap. All right, hang on. Let me get live cam. Whoop, whoop. Okay, there we go. Now I can do this a little bit better. So here you go. And you can see the machine. This is my monitor. That's some body armor stuff. Here's my Predator monitor. This is the setup. Here's my keyboard. Yeah. So this is actually the setup that I run when I stream to you guys every day, every class. So yeah, if you guys want to know what that looks like, if you're ever curious, then there you go. Hopefully, I've satiated a bit of your curiosity. You know, oop, there we go. So, I mean, it's a good box. It does exactly what I want it to do. I was playing Baldur's Gate 3 today, so it ran beautifully on this machine. So, well, when you profit monies, I mean, it's really not that hard, to be perfectly honest. So, especially money that you don't spend very often. So, there are essential things in life. This box is one of them. I mean, it's kind of true. Adjust this camera here. Okay, hopefully I got that boopers. All right, there. Something. All right. Okay, so today, you guys, let's talk about what we're doing today because we're getting started a little late here today. All right. So just to again, I want to just again apologize about what happened last time. That is completely on me. I obviously didn't want things to work out that way. But it kind of is what it is, unfortunately. In other news, today, surprisingly enough, what I was going to do on Wednesday was this was going to be the last chapter of the textbook. So if you're in the 8-week class, this would be the last new material here actually for the textbook. So yeah, chapter 10, that's it. And then we talk about the test and all that stuff, next week. So that is what's on the agenda here for today. All right. So let's go ahead and get going here with that. All right. And we'll see what we can do. All right. Yes. Eventually I'm going to get this going. Okay. Yeah, as you can see here, pretty much a lot of things are different. So, okay. In any case, so today in section 10.1, so let's talk about section 10.1. By the way, are there any questions from you guys before we totally get started here? We'll talk about the test and the final and all that stuff. So, okay. So in section 10.1, let's at least talk about this here. Today we're going to be talking about angles and right triangles, okay? So one of the things that we talked about here in angles is we discussed, of course, types of angles like acute and obtuse and right angles and straight angles and the whole 9 yards. We talked about that in the last chapter. Do you have a practice test for the final? I can make one up. That's not a problem. I'll just have to take a little time to do it. That's all. I can make one up for the final. That's fair. Um, I believe the final is like 50 questions, so. All right. Okay, so we talked about angles previously. Now, angles here, we discussed about one certain aspect about angles that we talked about was degrees, minutes, and seconds. And they talk about this in this particular section as well. But just as a good refresher here, remember that for degrees, minutes, and seconds, remember that again, 60 minutes, or actually I just put 60 minutes here, just the abbreviation. 60 minutes is equal to 1 degree. All right. And 60 seconds, of course, is equal to 1 minute. So, All right, so that isn't too hard to figure out. I mean, pretty easy if you ask me. Usually, again, based off of time. So it should be. I put that in the wrong place. Okay. All right. Now, a couple of things that we need to talk about here, of course, are the other two parts of when we talked about degrees, minutes, and seconds. So one of the things that we talked about here specifically is that we can also represent this in a different manner, i.e., the thing that we want to specifically talk about here is that 1/60th of a degree is equal to 1 minute. And more specifically here as well, 1/3600th of a degree is equal to 1 second. So let's say, for example, why is this important? Well, let's say, for example, we want to convert a decimal degree to, say, a degrees, minutes, and seconds. So let's talk about how we can do that. So we'll go with a decimal degrees to degrees, minutes, and seconds. So let's look at some examples here about how to do that. It's really not that hard, but it will require your calculator to do. Otherwise, it won't make any sense. Okay, so I'll write down a random, example here. It doesn't really matter what I choose here. So let's go 89.24697. Okay, so this is our random degree measure, 89.24697 degrees. And we're just wanting to put this into degrees, minutes, and seconds. Okay, so the first part here that we want to do that right away is, of course, you can separate the 89 degrees because essentially 89 degrees is going to sit there and do effectively nothing. It's just there. However, the part that we want to focus on here the most is going to be the decimal part. Okay, so that's the key here. The key here is to focus on the decimal part. Okay, there's a second key here. Key number 2 is, with the decimal portion here, the 0.24697, multiply by 60. Basically, you're going to be multiplying by 60 twice with each respective decimal portion. Let me go ahead and describe what this means. So I'm going to take 0.24697 and I'll multiply that by 60. And this is going to get me the number of minutes. So I'm going to bust out the calculator here. And here we're going to get 14.8182. So understand I'm keeping the 14. Okay, so I'm keeping the 14. However, again, just to reiterate here, we now have 14 minutes. All right, we have 14 minutes from what we found in this part. Now I'm going to do this again, but this time with the 0.8182. So I'm going to take 0.8182 and I'm going to multiply that by 60. All right. And then I'm going to get an approximate answer here, of course. So not an exact one, but an approximate one. And here we get 49.092, or again, we're just going to take, again here, 49 seconds. So you can see exactly how we can put it together. Here again, we just multiply by 60 twice with each respective decimal portion as a part of the thing that we're given here. All right. It's not too hard when you work from decimal to degrees, minutes, and seconds. It's actually fairly straightforward without too much trouble. Okay. So we got that. All right, questions about that so far? Any questions, anybody? No? Okay. All right. Okay, let's go ahead and do the next example here. This time we'll go degrees, minutes, and seconds. So degrees, minutes, and seconds to decimal degrees. Okay. So with degrees, minutes, and seconds to decimal degrees, let's pick a random example here. Let's go with 25 degrees. 34 minutes, and 34 minutes, I'll put it with this, 34 minutes and 12 seconds. Sure. All right, so 25 degrees, 34 minutes, and 12 seconds. We're trying to convert that into a decimal degree. So for us to do that here, first and foremost, we're just going to add a few things. First of all, we have the 25. But we're going to add two more quantities to it. So what's the key here before I go ahead and state it? The key here is to divide the minutes by 60 and the seconds by 3600 and add together. So what we're essentially doing here, it's very simple. We're effectively doing this. We're doing 34, sorry. I'm thinking 25. 34 over 60. And then we want plus 12 over 3600. And we just want the decimal equivalent since that's all we want here. So putting this together here, again, as you can see, it's pretty easy. So what we'll get here is 25.57 is what we got here. Okay. Okay, and that's how we can get that decimal degree. No problem. Okay. Questions about that? Hopefully that's not too bad. Nope. Okay. Perfectly fine. Okay, just checking. Oh, okay, that's fine. All right, that's okay. All right, next, let's talk about another degree measure here. So you're saying, well, there's degrees, minutes, and seconds, but you're telling me that there's another degree measure. You're telling me that there's more to know. I'll be like, yes, unfortunately. So what we're going to talk about here is now called the concept of radians. Now, radians is going to be important in certain applications, and we'll take a look at that momentarily. But first of all, what exactly is a radian? So a radian here is basically another representation of degrees. Okay, another representation of degrees, again used in various calculations. There is an approximation of radians, but we want to talk about how to convert degrees into radians specifically. Okay, so converting degrees to radians is a actually pretty simple task. So all you have to do here is, let me grab that. Oh man, there it is. Grab the new math type here. Okay. So to convert degrees into radians, what we're going to do is we're going to take the number of degrees. So actually, I'll put that all in math type. Yeah. So we're going to take the number of, actually, let's do this here. That's nice. All right. So we're going to take the number of degrees and multiply it by pi over 180. So we're going to multiply it by pi over 180. Okay? So this is our little formula here in order to convert degrees into radians. Now, I want to show you something here very important here. So we're going to do an example, and I want to kind of showcase what it should look like when you convert degrees into radians. So let's go with the premise here of 150 degrees. All right, so let's just do that. Okay. So 150 degrees, and our goal is to convert it into radians. Now, if we want to find the number of radians here, the radians here are going to be 150 times pi over 180. Now, you're probably saying, well, yeah, Ali, that's really easy. It's exactly what you showed us, so why bother reiterating this? Well, it's actually how the answer needs to be written is actually the more important part here. Although you can on a calculator do 150 times pi divided by 180 and get some random decimal number, and that part is true, that's not what we're after here necessarily in every case. What we can do is reduce down 150 over 180 as a fraction and leave the pi alone. All right, so if I just do that really quick and I reduce the fraction, what I actually end up, and you'll see in most textbooks, is I'll actually end up with 5 pi over 6. So if you see here, I reduced the fraction down. I didn't actually go ahead and multiply the pi out. Okay. So if we take a look at this here for our example, hello, welcome back. All right, so if you take a look at our example here, you can see we get 5 pi over 6, okay, in this instance, all right? So that's the way that I would like you to write it and that pretty much the book would like you to write it. So let me put a big note that goes with this here. All right. All right, so reduce the fraction and keep the, I should probably put pi here. So you got to reduce the fraction and keep the pi, all right, if you can, so if possible. Some cases you may end up with a decimal because it's just still, there's no really fraction to reduce. Okay, so, which is totally understandable, but we usually try and keep the pi as much as possible. Now, one very important aspect about radians that we do need to talk about here that we will be using is that if we're talking about 360 degrees, okay, we talk about 360 degrees, well, we're going to use a little conversion here. 360 degrees, i.e. 1 revolution, which is pretty common for us to use. Oh. Actually, we'll make this. All right, very important for this one here is going to equal specifically 2 pi. Okay, so 360 is equal to 1 revolution, which is equal to 2 pi radians. I'll actually put 2 pi radians here just for... Okay. Oh, okay. What do I mean by if possible on the note? Okay. That's a fair question. So basically what I'm trying to say here is that not every problem is going to necessarily be able to reduce fractions down. I'll give you a good example here. A good example is if we wanted to convert, I don't know, let's say I'm trying to think. Uh, yeah. Okay, so let's say I went with the example here, Gustavo, of 55.3565782, whatever. Okay, converting that to radians is going to be incredibly messy. And you would notice that I couldn't, really reduce that down with 180 and keep the pi. So it's just sometimes better just to multiply the 55.36 blah 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 times pi and divide by 180 to get the number of radians. In other cases, it's okay to reduce the fraction and keep the pi, which makes things a whole lot more cleaner if we can. So that's kind of the meaning behind the note that I was talking about there. There any other questions about that, Gustavo? It's just like, that's basically how we take it. Cool. Excellent. All right. Now, of course, we can go backwards from radians to degrees as well. So let's go ahead and talk about that. All right. So radians and degrees, pretty, pretty, pretty simple here. All we have to do is just go backwards. All right. So we're going to take degrees is going to equal degrees is going to equal radians, and then we multiply that by, instead of pi over 180, flip it around. So you're gonna get there. Okay. Actually, I don't know why I need that. All right. So we just do 180 over pi, and there we go. Okay, so very simple, as you can see, fairly straightforward. So if I wanted to find out, let's show, let's see, what's a good radian measure? All right, so let's go with 3 pi over 2. Okay, so let's say I had 3 pi over 2. And I wanted to, I asked you, well, how many degrees is 3 pi over 2? Okay, so then the number of degrees here is going to equal 3 pi over 2 times 180 over pi. Now, fortunately for us here, the pi's will cancel out, which is great because, well, we don't want that extra number floating in there. That means the rest of it we just have to kind of figure out. We take 180 times 3, which is 540. 540 divided by 2 is 270 degrees. So that's 3 pi over 2. Okay. What the heck? Okay. Sure. I have no idea why. All right. All right. Any questions about that? Questions at all? Nope. Okay. Let's keep moving forward then. No problem. Okay. So next, it's out of here. All right. So next, let's talk about applications of radians. So I mentioned it here before. I said, okay, well, what about applications of radians? Let's take a look at that. So the first application of radians here is going to involve the sectors of a circle and arc length. Okay. So exactly, let's go over arc length first. What exactly is arc length in particular? So first of all, arc length, ah, 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 ah. Arc length is equal to the radius, again, the arc length of a circle here. So the radius um, times the central angle in radians. Yes. This is also abbreviated as S is equal to R times A. So you'll see that kind of abbreviated like so. All right. Now, one thing I want to point out here is exactly what does arc length mean in terms of, say, a picture. Okay, so we have, okay. So here's a circle. What we're effectively finding is we're finding from, say, we're saying here's the radius. Let's say this is our piece of the pie right here. This is our central angle A is right here. And then essentially we're finding this length from here all the way over to here. All right. Arc length. Okay. 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 So that's essentially what we're trying to find. So think of it as like I want to find the length of the crust on the outside of a pizza slice. That's what I'm trying to find. I'm not trying to find the entire pizza slice. I'm just trying to find the length from one end of the crust to the other end of the crust of the slice that I just took out of the whole pizza. I can do that. Okay, no matter where the cut is, as long as that cut goes to the center, then you're fine. All right. So what we're going to be doing here is figuring out how to get that arc length here, but we're going to be using that for just one more thing. We'll be using that actually in a couple of things, but let's also talk about the one other thing here, and that's the area of a sector of a circle. So we talk the area of the sector of a circle. That's going to be a different formula here. So the area here is going to equal specifically 1/2 times the radius squared. Actually, probably, you know what? Yeah, okay. I got it right here. Might as well just use it. 1/2 r squared times a. So this is the area here in this instance. So okay, so this is what we have here. R and A have the same meaning here. Again, R is the radius, A is the central angle in radians, all right? So no difference here, but I'll rewrite it here just in case. If you missed that the first time, then I totally get it. So again, R here is the radius, and A is the central angle in radians. All right. So that's what we have there for the area of the sector. Now, just to highlight here, what's the difference? The difference is that now we're actually finding the area of the pizza slice itself is essentially effectively what we're doing. So we're actually finding this entire area here as opposed to just the outside. So that's what we're doing here in this particular instance. Okay. Okay. All right, we're going to do some examples with that, but I just want to state those two formulas. Those are the first two. We have a few more to go. Okay, the next two formulas here are two formulas you probably wouldn't expect here with radians to use, but still nevertheless very important. The first one is linear speed. Now, most people are pretty familiar with linear speed in some form or fashion. Okay, whether it says, okay, the car's going 100 kilometers an hour, okay, or 60 miles an hour, whatever the case may be. All right, so like, all right, it's going that fast. Fair enough. Okay, but what we want to focus on here is how to find linear speed. Now, of course, there's two ways to find linear speed. So let's at least focus on that, and we'll talk about the lettering. So the classic one that everybody sees is V equals D over T. This is the most classic of classic formulas that you definitely see a lot of times. So exactly what's V? V is just another way for velocity or linear speed. So yeah. Oops, sorry. So V is equal to velocity slash linear speed. All right, D here is our classic distance. Okay, and T is time. Of course, time is dependent on context. All right, so time could be in hours, minutes, seconds, whatever we're working with. Just depends on the context, like as usual. Okay, and while that may be fine and all, it's I mean, I don't know. The best way to put it is it's okay. It's not like the greatest in the whole wide world. I guess it's something that we're very used to, but I yeah, it's just definitely one of those things. Well, we're gonna might expand on that in just a little bit. So just hold on to your hats for that one. Okay. Now we're gonna add a little bit to that, so that's fine. All right, now linear speed has a counterpart, a very important one at that. So this next one here talks about specifically what we call angular speed. So linear speed is basically how fast the car is moving, say, in a straight line. However, angular speed is basically how fast, let's say, that object is moving, while, say, how fast are the wheels turning necessarily, because they could be turning faster than the actual object traveling in a straight line. So the wheels are moving possibly faster. What's the angle? We are talking a bit of drifting. This is true. This is true. Gotta know some drifting, There you go. If we're gonna drift in Hakone, hey, that's what you gotta roll with, bro. That's how it works. So let's all right, if you want to see real drifting, okay, you could look there's real drifting, all right. We could watch a video on drifting since you mentioned drifting. All right. I'm telling you, there is definitely real drifting that actually happens. Oh, that's not real drifting. That's BS. All right, let's try. Where is it? Oh yeah, here's a one for Toyo tires. All right, there's your video right there. There you go. There's your video of drifting. Everybody likes drifting. Hey. Yeah, those roads are real. Yeah, they do look like that. Man, it's like almost perfectly made. Those guardrails are no joke either. All right. Good stuff. All right, let's go back to angular speed. I'm sorry. All right. So what is angular speed? Let's talk about angular speed. We'll write down the formula for this. We'll have W is equal to A over T. Is that the one you... Okay, that is not the one you used. Okay. All right. So let's at least describe what each of these letters mean. It's not too bad. So W here is angular speed. A is the central angle in radians. And T is time. All right. Now, one of the important things is that you can actually express linear speed in terms of angular speed. So one of the other formulas that you actually have here is you can determine linear speed of like this. So you'll actually see, how do you get distance here? This can be rewritten as, and I better write that down. So linear speed can be rewritten like this. It can be written as R times A over T. So rat. Okay, so this is another way you can express linear speed, is radius times the angle and central angle in radians divided by time. So that's what the other two are there for. All right. Okay, so that's another formula in the books for you. Okay, angular speed, and then of course linear speed. You get the general gist. All right. Now, there's one more formula in here that most of you probably do know here rather well. You probably have heard it at least once, and this is in reference to right triangles, which we'll explore a lot more in the next two sections. But this has to do with the Pythagorean theorem. So I think probably you've heard the Pythagorean theorem at least once in your life. I mean, it came up probably a while ago. If it's been a while, I totally get it. But the Pythagorean theorem is, used everywhere when it comes to engineering, when it comes to pretty much everything, because of course it runs off of the idea of the right triangle. So here's our right triangle. So there's our right triangle, just like so. We have three sides to the right triangle. All right. So we have, again, A here. We have B here. And we have C right here. Okay. Now, the Pythagorean theorem says if we take a squared plus b squared, that's going to equal c squared. Okay, so not hard to obviously figure out. You guys have seen that hundreds of times maybe by now. Let's at least formalize it in here though. All right, so we got that. All right, good. Okay, so we'll probably use that more in the next section to some degree. Yeah, maybe. All right. In any case, let's go ahead and take a look here at some triangles, and we'll also take a look at some application problems as well in this section. Okay. Let's go to 6. Actually, let's just do, you know what? Because we're going to do that today, I think I'll just skip right to the word problems. And we'll look at the, or actually, some of the word problems. Okay, let's go ahead and take a look here at a couple of these problems here. All right. Let's look at question number 1. All right. So let's look at question 1 here. It says a transition duct is constructed from a circular sector of radius 18 and a central angle of 115 degrees. What is the area of the metal used? Letter B, calculate the arc length of the sector. So essentially what it's asking us here is what's the area to construct this particular transition duct, i.e. the area of the sector of the circle that's been properly cut out. So the question is, how do we go about doing that? What should we do? What should we do here, guys? Ivan, Gustavo, Diego? What do you think? Not sure. Okay. Let's take a look here. So if we were to look at our formulas here, which formula would match the best? We're doing question number 1 here. Okay. So we're trying to find the area of the metal used here in this question. So can anybody tell me what would we use? The area of the sector. Okay, good. Let's use the sector formula. Excellent. Okay, so now that we know we're using the area of the sector of the circle, all right, so we have that. That's fine. Now the question is, okay, if we're doing that here in this problem, what numbers are we going to use here specifically if we're using this formula that we have here? Radius, okay. What's our radius equal to? Radius is 18. All right, so that's fair. All right. What's our angle? What's our angle here? Let's take a look here. It says angle A is a central angle in radians. Aha, okay. The central angle is 115. All right, very not so good. All right, so this is the one thing that why I asked this question here as deliberate as I did is because this is the most common trap in these problems. So A here is the central angle in radians, okay? In radians. All right, so that's actually kind of a big thing here. So 115 is 115 degrees, but not 115 radians. Those are two different things altogether. So the one thing that we have to make a note of here is note you must always change the central angle from degrees to radians if you are using these formulas. So this is probably the most important part here, is that we are forced to change 115 degrees into radians and then apply it to the formula here. So that's what we're going to do here in this instance. So let's see how that works out. So I use A is equal to, again, 1/2 r squared. So r here is going to be 18. Now we just have to figure out what 115 is in radians. So the number of radians in 115 degrees. How do we change radians to degrees again? How do we change 115 to radians? Okay, multiply by what? Okay, good. So we're going to multiply by pi over 180. That's correct. Okay, now let's reduce this down. I'm going to take 115 over 180, just reduce that down into a fraction. Okay. So this is this is going to be 23 pi over 36. Okay. So we're going to take this and we're going to multiply it by 23 pi over 36 to get an answer. I'm going to plug that into the calculator there. All right, anybody got an answer for me here? What's this equal to? You're going to get a decimal for this, by the way, so. You got to remember the parentheses here. And did you do 18 squared there as well? So this is what I got. I'll show you what I got. I got, I got 325.155. That's what I got there. So if you take 1/2 times 18 squared and then multiply that by 23 pi over 36, then you should get this answer just like so. Because if you're not sure, just take it in 2 steps instead of 1. That's what I normally do. All right. So that's the first one out of the way. There we go. Okay. All right. Let's look at the next one here. Okay. All right. Let's take a look here at another problem. And I want to be sure I got that right. No. No. All right. Make sure I got that. Okay. So let's look at where is it here? Not that one. There we go. So let's look at number 8. Yeah, number 8 was the one I wanted to look at. So number 8. A pulley with a radius of 36.2 centimeters rotates at 6.5 revolutions per second. Find the linear speed of the belt driving the pulley. Okay, so we want to find that linear speed, and we're given the radius, and we're given here how many revolutions per second that it happens to go around. Okay, so this one here is actually not as bad as it looks, because it looks like you don't get a lot of information, but in reality, you actually do get quite a bit of information. let's go ahead and take a look here and see how that works out. Now, you remember what we did here is we went ahead and if we're going to use the formula here, we're going to go ahead and use the formula for, what should we call it here? The linear speed here. So linear speed here is going to equal, shit. We're going to use the alternate form of the linear speed. If you recall here, the alternate form here is radius times the central angle in radians divided by time. So the question is, well, exactly what are we going to come up with here if we're taking the radius times the central angle divided by time? Well, we're given the radius here already. All right, so the radius here is 36.2. We're going to multiply that by A. A is going to be 6.5. Now, understand what the 6.5 means, okay? So we have 36.2 centimeters. 6.5 comes in at revolutions per second. These are the units here. We have, man, that looks terrible. Gosh, what am I doing with my life? All right, let me do this again. Sorry, everybody. So we have 36.2 centimeters. 1 times 6.5 revolutions per second. Now, the last part of this problem here is actually fairly easy. We had stated earlier how many radians was in 1 revolution. So once again, I'll ask the question of you guys, how many radians in 1 revolution? How many radians in 1 revolution? All right, it's equal to 360, but I mean in radians, not degrees. How many radians is going to be 1 revolution? All right, 2 pi. So we're going to multiply this by 2 pi. So, yeah, God, darn it. All right. All right, I'm going to get better at using this thing, but I'm really bad at it today, apparently. Okay. Let me put 6.5 here. Okay. And I'm going to multiply this by 2 pi radians. And then this is like one more conversion here. It's Friday, it's true. It's true. We could cancel out the revolutions. Now, the radians don't effectively do anything in terms of your final result here. So you're just going to take it straight across here, 36.2 times 6.5 times 2 pi. Let's go ahead and get that done quick. All right, and then finally we get our answer here at 1,478.43 centimeters per second. So it's going rather fast. Okay, and that's our final answer for that. Questions about that? Yeah, I know. Okay. All right. Yes. All right. Getting down to the final throws here. So let's go ahead and take a look here at the last couple of sections here. Okay, and we'll go ahead and put it together here, hopefully. All righty. So, section 10.2 is going to be where well, obviously we talk about radians, but section 10.2 is the real meat and potatoes of this, what we're going to be talking about here today. How many sections we got left for today? I mean, we're doing the last 2 sections of the book, so I'll leave it up to you. Do you wish to do the last 2 sections of the book? I mean, we got 1 week left. It's up to you. I don't know. Hey, you guys have made the effort to come out, so I have an obligation to ask. We have a whole week of classes left after this. This next week is the last week. If you're in the 8-week class. Okay, if you're in the 16, you're perfectly fine. You shouldn't have a problem. If you're in the 8, then yeah, these last 2 sections will matter. I'll be going over these sections anyway in the 16 anyway, so, you know. Okay, now for pretty much this entire section in section 10.2, is going to be done here on this little paint guy. So, because we need to understand, yeah, okay, totally understandable. So we're going to look specifically at right triangles, okay? So right triangles is going to be our way to be, all right? So here's a right triangle. Yeah. Right triangle forms a perfectly 90-degree angle here on the side. Okay, now, there are sides to the right triangle. We talked about that before when talking about the Pythagorean theorem. So for example here, we have A over here, we have, say, B over here, and we have C over here. Okay? Now, there is something important that I do have to say in regards to this, which I will point out here, but we also have, remember, we have 3 angles here as well. So we got 3 sides here, but we have 3 respective angles that go with their respective sides. Now, exactly how does it work with the triangle? You know, how do you know where to put A? How do you know where to put B? And how do you know where to put C? And then how do you know where all the other angles go? Well, that's where this part actually comes into play. So so we're going to put a little note here. Put note, all respective angles are opposite their respective sides. So this is always true. All respective angles are opposite their respective sides. Meaning to say, if A is over here, then what we're going to do is we're going to put big angle A over here. So you'll notice I'll use small letters for sides, capital letters for angles. Big B is going to be over here. So there's big B. Poorly drawn, but okay. And then lastly, we have big C here, which is the actual right angle itself. So there we go, big C. So you say, okay, big A, big B, big C. There you go. You got it. You're good to go. All right. So this is how we set up every single triangle. All right. So this is the setup for every single triangle, just to let you know. All right. And I probably will add another text box. Why can't I put a text? Let's go. Thank you. Please. Oh my gosh, this is such a pain in the ass. All right. Like I'm trying to do like the thing and it's just like, oh, I don't want to do the thing. I'm like, oh, bro, please do the thing. All right. Now the question is, why am I showing you this necessarily? Is because this does actually have this is actually super important, okay? So just to let you know, this is how we're going to go to the well like a ton of times here when it comes to say doing this stuff out. Now, we have to also acknowledge a couple of other things in this section, and then we can get to the last section here as well. So the other couple things that it's like, okay, we have a right triangle. We know how to set them up now. We know what the respective sides are. Okay, fine. But what do we do with those respective sides? What are we doing with these triangles? Well, that's where the trigonometry part is going to come into play. So let's talk about trigonometry and how it works here. And then you can hate me after that for evers and evers and evers. Okay. What do we want to call those? Yeah, that's right. All right, so here we're going to be doing trigonometric ratios. Okay. So specifically here in this instance, what are we going to be looking at here? Well, if there's one thing to recognize about trigonometric ratios, we're going to be going over the acronym here, SOHCAHTOA. And you may have heard of this before. So if you've seen this before, what I'm going to present to you should be nothing different. Okay, but if you've never heard of this before, or it's been a very long time, this will be a good refresher over some of those trigonometric identities. I will put a note here, a separate text box. Okay. All right. Note, this is only applicable for right triangles. Okay. This is not applicable for any other types of triangles, just right triangles. Okay, let's make another right triangle here. There we are. Okay, so we have a right triangle here, no problem, easy peasy. Now we have three main trigonometric functions, okay? So let's talk about our three main trigonometric functions that we normally use. If you're an engineer, you're going to use a lot more than that, but we're only using three of them, so that's the only three we happen to care about. All right, first one here, S, S-O-H. S stands for sine. Now, specifically here, I want to point out a sine here, sine of what? Because we're taking the sine of a particular angle. And that angle I'm going to put is letter X. I'm going to put it right here. So this is the angle X or the angle theta, whatever you want to call it. This is the angle that's inside the triangle that we're testing over for each one of these examples. So we have sine of x here, and we have O and H. Now O represents the opposite side of that of the angle. So O here is opposite. Dang it. What? Put more text. All right, so there's the opposite side right there. No problem. Okay, now, so that's going to be opposite, and let's put this as equals. Okay, then we have H. Now, what is H here? H is referencing the diagonal here between these 2 points, which is what we call the hypotenuse. Okay, so we call that the hypotenuse of the triangle, specifically. So this is the hypotenuse of said triangle is right here. So opposite over hypotenuse. All right, so that's sine of x. So just to point out a couple of things here that we'll add to the text. And I'll put it down here. Remember, opposite is the opposite side to the angle. All right. All right. So that's side. Let's look at the next one. We have CAH. So C is what we call cosine, or COS. And now we're going to take the cosine of that angle. Same angle, x, but now we have an A thrown into the fray. Well, we do have a meaning here for A. A here means adjacent. Okay, so adjacent is just a fancy word for saying next to. Okay, it's just a super fancy word here. So there's adjacent. There's anything to write home about, but again here, just to reiterate, adjacent is going to be equal to the side next to the angle next to the angle. All right. Okay, so in this particular instance, it's going to be, again, adjacent. I'll label it as ADJ, adjacent, over hypotenuse. I'll label that as HYP. This will be OPP. Okay. Finally, we have T. T stands for tangent. So we have tangent of x. So O and A represents the same O and A. O is opposite, and A is adjacent. Okay. All right. So there you have sine, cosine, and tangent here based on the right triangle, with these sides being our triangle. However, and I do want to make a strict note about this here. This is very important. Okay? So opposite and adjacent can switch depending on which angle that you're looking at. So let's say this is angle X. Let's take another 2D right triangle here. Let me show you what I'm talking about. If this is a right triangle, okay, and the reason why I point this out is because I want people to not get confused. So let's say this is our right triangle here, okay? And we're asked, okay, if we're looking at that right triangle, we want to see each side here. Well, let's say I'm looking at the specific angle up here. We'll call that angle Y. Well, then suddenly with angle Y, over here becomes the opposite side. So opposite becomes over here. And the adjacent side actually is over here to the left. The hypotenuse stays the same. The hypotenuse is always the same. But it's adjacent and opposite that switch because it depends on the perspective of what angle that you're looking at here. So that's the one thing that you do need to be careful about there. So you need to be careful about what angle you are working with. Okay. Okay. All right. Are there any questions about that so far? No? Okay. Well, let's look at some examples now. Okay. And let's see what we get here for some of these problems. All right. Can I move the screen to the right? Sure. Are you talking like this? Did I get it right? Or did I make it worse? Oh, okay. I think I know what you're talking about. Let me see here. Yes. So like over here. Oh, you want to see the last note? Okay. Well, there it is. It's over here. It's all over here. Yeah. And then a tangent here. Let me put tangent over there. I'm making things pretty horrible right now, so sorry. Okay, there we go. Just let me know when you're done, then we'll move on. It was your phone? Aw, man. Sucks. Okay, good stuff. All right, let's go ahead and let's look at the next one here. That's nice. So let's go over the next part here, which are some sample problems. We're getting there. Here we go. So this page is page 6. Okay. Okay. Really? Oh, yeah, at the bottom. Okay. So let's take a good look here at a couple of these problems, and we'll see exactly how to work with it. Obviously, some of these need the calculator, but let's look at just one of these, one or two of these, and then we'll move forward. Okay, so they give you the sides of the triangle. That's all well and good. But let's see, how about number 3? Number 3, what is tangent of 23 degrees? So using our rules for right triangles that we just talked about, What is tangent of 23 degrees according to this triangle? So what is tangent here? What's the definition of tangent? So let's look at this here. What's the definition of tangent? Opposite over adjacent, okay? Now, what number is opposite to the angle? 5, okay, right. What number is adjacent to that angle? 12. So put it together, and what you're going to get is 5 over 12. And that's your answer. So according to this problem here, tangent of 23 equals 5 over 12. So that's the opposite side over the adjacent side according to this picture here. 13 is the hypotenuse here, not adjacent. Remember, adjacent is just a fancy word that means next to, but it's not the diagonal of the triangle. Hypotenuse is always the diagonal of the triangle. Let's try another. Try the previous one. No, not the previous one, maybe. Um, yeah. Try sine of 33. What's sine of 33? Yeah, again, it's all about perspective here. Sine of 33 in problem 1. All right, nice job, Ivan. That's correct. 27 over 50. Yes, very nice. So 27 is opposite that of 33 degrees. All right, and 50 is the hypotenuse. Opposite over hypotenuse. Done. 27 over 50. Nice. Okay, so far so good. All right, good, good, good. Okay, now let's look at the next page here. Okay, now there are other types of problems here, and I'm going to point out just maybe one of them, a couple of them, really not a super huge deal. Anyway, on your calculator, if you have a graphing calculator, I don't know what type of calculators you guys got, but if you have a graphing calculator, you want to make sure that your calculator is set to degrees and not set to radians. If you see like an old school calculator, it says RAD at the top, and that represents that the calculator is set to radians. But if you have the old school calculator and you see DEG at the top, that means that the calculator is set to degrees. Okay. Now, if you're on the graphing calculator like mine, my super old school one, okay, that hasn't been changed in many, many years, I'm going to go ahead and hit the mode key, and you'll see underneath the mode key here specifically, the mode key has a bunch of options, but it does have one option for degrees and radians, and it'll be defaulted to radians for whatever reason. So just switch that over to degrees, hit enter, and then quit that menu by hitting second in mode to get out of the screen. And therefore your calculator here for a graphing calculator will be set to degrees, which is what you want. Now, what we're going to be doing with those degrees, as you can see here, is just effectively finding each of these particular trig values. These are just pure calculator-based problems. It's really not too hard to figure out. So if you say, hey, what's tangent of 12, just literally in your calculator, type tangent of 12, and you have your answer. Yeah. However, on the other hand, let's look at the other half of things. So let's take a look here at a couple of problems here that actually do matter. That's part C here actually has a lot of different types of problems about how we want to deal with finding an angle if we know the value of that particular trig function at that angle. So let's go ahead and do one of these here really quick. So we'll go ahead and do cosine of A is equal to 0.662. Okay. Okay, now here's the problem. All right. So 0.662. Okay. Now, normally in algebra, we would go ahead and, say balance, right? We would divide by things on both sides. And effectively, that's what we want to do. Unfortunately for us, we are not allowed to just divide by cosine. That's not how it works. The reason why is that cosine's not a number. Cosine is a very special function that has its own unique definitions. So we don't want to be dealing with a function here to divide on both sides. That gets to be very messy very quickly. So how can we quickly go ahead and do this problem? Well, we're going to use another key on the calculator here. In this case, we're going to use what's called, let's go ahead and put that in red. We're going to be using cosine inverse. So cosine inverse is the second key or the shift key and the cosine key, which should pop up with cosine inverse. Now cosine inverse and cosine, this is the way you kind of effectively eliminate, they effectively divide functions. So as you see what you're left with A is equal to cosine inverse of 0.662. Okay? So if we do that out, that's going to be, in this case here, 48.55 degrees. Okay? And that's what we get here for this particular problem. Are there any questions about that? Any questions at all? Okay. If you have a TI-84, make sure, is it set to degrees there, Ivan, first and foremost? So go to mode on your calculator. Okay, good. So hit the second key and hit the cosine key. Okay. Then enter the number next to it. So it'll say cosine inverse on the top there. Okay. So it should say 48.55 degrees. So if it does, then we're good. Okay, there we go. Yeah, you got to use the correct one. So you just got to be a little careful about that. Oh yeah, okay, that was the problem. Yeah, tangent has its own deal, cosine has its own deal, sine has its own deal. So yeah, just be a little careful about that. All right. Solving right triangles. Oh boy. Okay. So tired. All right. Oh man. I want to finish this, but I'm super tired. I don't know why, but I'm just like super sleepy. I'm gonna take a nap, man. Well, then again I've been up since 7, so or 8, 8, yeah, 8 actually. Napped at noon. Fair enough. Fair enough. Hmm. Well, I'll tell you what. Tell you what, guys. I'm gonna save this for Monday. Is that okay? I know it's last week, but I do have a couple things I do need to talk to you about anyway. So I'll save this last section for Monday. Oh, okay. If you're in the 16-week class, you're set, man. Gustavo? Gustavo, I know are you in the 8-week class, right, Gustavo? Yep. Help me help you, brah. Help me help you. Where are we lost, my friend? Let me know, Gustavo, where are we lost so I can help, okay? All right. I'm not sure what Gustavo's up to. I'm gonna guess that Gustavo's really lost in the ether somewhere. I have no idea. Okay. So here's what I'm gonna do. Okay, let me talk about the 8-week course here. Okay, don't worry. I'm gonna cover the last section here on Monday for you, Gustavo. So just come on back. Now, for the people who are in the 8-week course, this is going to be a more of a formal announcement here. Is that there's going to be a second test, excuse me, over chapters 6 to 10. All right, that'll be due on Sunday. So next Sunday is when that test will be due. So chapter 6 to 10 test is due Sunday. Let me check the date for that. That is the 18th. So that's the 18th. And the final is due the 19th. Okay. For all 8-week members. Okay. I will put up a practice test this weekend for you. Okay. For the test and the final. All right. Now, one more thing for the people in the 16-week class. The first test will be open until let's see, until this next next Sunday, or not next, yeah, next Sunday, right? Yeah, that's what I planned. Yeah, that is what I planned. Okay, so the first test is gonna open up. Probably I'll open it up tonight or something like that, and it won't be due until next Sunday. So yeah, pretty much the 18th. So just to let you know, if you're in the 16-week class, like I know 2/3 of you are here, then first test will be open until the 18th there. That's correct, yes. That's over chapters 1 to 5. So that's for the 16-week classes, just over chapters 1 to 5. Yeah, if you've done it already, then you're already ahead. But if you haven't, then I'm going to reopen it, and it'll be open until next Sunday. So that's what's going on. All right, any questions, guys? No? Okay. So I'm going to wrap up here for today. We're going to finish off the last section here for next time. I'm just a little tired. Thank you very much, Diego. All right, you guys. You guys have a wonderful night. 2 quizzes. What quizzes? You mean the 2 practice tests? If that's what you're referring to? Yeah, the practice tests I'm going to be putting up, I have to make them up. But yeah, I have the tests. I just have to match the practice test to your actual test. So yeah, I'll put those up and you guys can work on those as many times as you want until you're ready to take it. So yeah, that should be pretty much it. All right, cool. Cool beans, everybody. All right, I want to thank everybody again for coming out. Thank you, you three. You guys are awesome. Okay, I'm so glad that you guys decided to come out. I know I want to. I'm so sorry about what happened on Wednesday. You know, that's not. I'm not making a habit of it. Okay, to try and ditch you guys. Trust me on that. I love coming out to this class, and I love having a lot of fun with you guys. So I'm so glad that you came out on a Friday just to come talk to little old me. I really appreciate that a lot, and I hope you learned something here today as well. In the meantime, enjoy your weekend, guys. You know, yeah. Well, don't worry. We'll be back to regular broadcasting next week. All right, I promise you that. You guys have yourself a very wonderful day. All right. I hope you guys take care of yourselves, and you guys have a great one. All right. We will talk to you later, everybody. All right. Take it easy, everybody. All right. Bye.